Next speaker, Naomi, who Ivana will introduce.
All right, and now I'm changing my hat, so I would like to welcome our next speaker on the stage.
Naomi is a Kempner Fellow at the Kempner Institute at Harvard University, but will soon be starting a faculty position at Boston University, so that's very exciting. Her work is extremely interesting in that it studies sort of model interpretability from a different perspective than most people in the field, particularly focusing on training dynamics, and as you'll see here, like phase transitions in language models over training time. So I am extremely excited about this talk. I've heard a variant of it in the past, and it's extremely entertaining, and I think you all will find it entertaining as well. So thank you, Naomi.
Hope this is a bit new to you, in fact. There's a lot of new things to talk about. I'm going to be talking, about phase transitions and, in general, about when you know it or you don't. And to be clear about this know it or you don't thing, there are like categorical concepts out there. We can say, all right, I believe that there are two types of people in the world on many, many different axes. Maybe you're a Scorpio. Maybe not, introvert, extrovert, righty, lefty, it doesn't matter. You have a sweet tooth or you like savory. But what happens if you have enough high-dimensional categories is that you can model a continuous space. And this is obvious, right? Because if you think about the way that computation works in practice, we're literally using a binary space, which is strictly categorical, to model a continuous space because we're using a computer. But what I'm going to talk about is that, in fact, if you have enough high-dimensional categorical variables, then you become, then it's sort of like you go continuous, and then that continuous space, because of how high-dimensional statistics and optimization tends to work, becomes categorical again. And that's extremely convenient for us from an understanding perspective for reasons I'll go into. One example of how this sort of categorical distinction between models comes up is in scaling. So in general, we know bigger models, bigger data, they both add to training compute time, and as we add compute, there tends to be a gradual improvement in model performance. You're probably comfortable with scaling laws if you're in the AI space. If you're not, then basically that's it. If you continue to add more and more computational power during training, you tend to also improve the model outcome. But we've seen some exceptions, in fact, which people call variously emergence or breakthroughs. Basically, there are situations where you have a task that has a sudden breakthrough at a particular scale during this scaling law. And that is a case of this kind of categorical behavior. So either the model knows this task or it doesn't. But we're going to go back into the continuous space just to start out to show that this is categorical, because we're going to look at how the distribution of performance changes with scale, the distribution across random seeds, initializations, different training runs. So if we look at one model run for each scale, which is the standard people tend to compute their scaling laws actually in practice by looking at one sort of a training run for each scale. Then we can see for this synthetic task, it's arithmetic addition. Don't worry too much about it. There's a very sudden breakthrough. So that must be when we hit the capacity for the model to finally do arithmetic addition. But not so fast. Here's another seed. And it starts looking very linear suddenly. It doesn't have this kind of breakthrough behavior. So because emergence claims tend to be based on scalar values, but the actual variation in performance is actually quite high, we might find different outcomes depending on our seed. So here we're looking at point A, the smaller scale right before the breakthrough. We're looking at this distribution of performances. And then at point B, larger scale, we can see a shift, a little bit of a shift, although the modes don't shift much. And you can see that if you sample from this very far to the left case, you don't know it. And if you sample from this right mode, you do know it. And if you sample from different modes, different components of this bimodal distribution, you're gonna end up with these breakthroughs. But you have the potential to sample from your successful component in both cases. So if you sample from the same mode in both cases, it looks linear. Okay, so that's kind of interesting, but like why? I would say it's interesting because these distributions change gradually, even as we see these big jumps in the mode measurements and in individual scales for single runs or even a small number of runs. What we're actually seeing is a gradual change in the probability of success, not a sudden breakthrough in capacity. And if you've read Saphra et al. And you're saying, oh, isn't emergence a mirage? I would say not. This is a continuous metric, and you can see that it is still basically bimodal in the settings where the original accuracy plots are bimodal, just to handle that situation. Okay. So that was a synthetic task, arithmetic addition, who cares? It turns out that even at like a decent sized scale, things that we consider to be emergent in large language models tend to have a similar distribution, bimodal distribution. So for multiple choice, which is pretty widely accepted as a emergent task because it's, there's a particular point where the model is able to handle the multiple choice format and compose it with its knowledge, we can see that mid-sized models tend to yield bimodal distributions in the sense that there is a, that this smaller model has this bimodal distribution while the larger model is consistently sampling from success. So that's another situation. You know it or you don't know it. And you can access both solutions, the solution that allows you to compose with the format and the solution that doesn't have that compositional ability. And the same is true in the data scale, since we said data and model size, both at the training compute, yes. At small amounts of multiple choice data, we pretty consistently sample from this failure component, and at higher levels, we pretty consistently sample from the success component, and in between, random variation again, bimodality. Why do I care about this and why should you care about this? Well, it means that we have a much better key to understanding these models than if we didn't have this kind of categorical behavior. So a lot of the scientific and theoretical work in training dynamics treats things as though they are smooth, that skills are learned continuously throughout training, that we always converge maybe with some little epsilon random variation, maybe a little Gaussian variation, and that as we scale up, improvements are gradual. And this is why everyone is sort of like interested in exceptions to this. Like maybe you've heard about grokking or, as I was showing you, emergence. But it turns out that certain concepts are natural kinds, as in the model knows it or it doesn't, which is huge news because we do not think in terms of smooth continua. We do not think in terms of the entire infinite space of continuous functions. We think in categories. So this is fantastic because we actually can know now the natural ways that models handle things and the things that are sort of natural kinds or concepts native to the model. So I was showing this like nice bimodality that happens as we transition. When does that happen? It happens near emergent thresholds. So that's good. We know how to find these natural categories of strategies. But maybe you're saying, well, I've never seen this kind of bimodality show up. I haven't seen this show up like at all. Maybe you've run a bunch of seeds for something and it looks Gaussian. And maybe even near an emergence threshold, it looks Gaussian. So I'm gonna show you how these can be hidden using a simple linguistics case study. So hierarchical generalization is a behavior that a lot of people have studied, where you train a model in a ambiguous setting, which is compatible with either effectively an n-gram model, a linear model, a simple one, or with a hierarchical model that actually reflects English language and most, maybe all, depending on how you feel about universal grammar, human language. So you can see that if you use the hierarchical model, in distribution, you get the same answer that the linear model gives you. But when you go out of distribution, only the hierarchical model is going to work. And out of distribution here involves cases where the inflection of the verb, so are here, is different depending on whether you use the actual subject of that verb or you just use the most recent noun. So here, the keys are on the table. You can just look back at the most recent noun. But the keys that unlock the cabinet are on the table. If you just look at the most recent noun you've seen, you're gonna say is. But if you actually can parse the entire structure, you're gonna say are. Okay, so I've introduced this task, and how is it that models actually end up tackling this hierarchical generalization? How do they sort of develop a bias towards hierarchical rules when they've never been exposed to these disambiguating examples? It turns out that when they're exposed to more complex data in general, and in this case what I mean is center embeddings, if you're interested, it is just cases where there's more than a single degree of recursion in a center embedding. That's what makes the model eventually develop this tendency towards hierarchical structures in its latent space. And that's kind of neat because it's what linguists would predict is used for language, like grammatical rule acquisition. But it's also interesting, I would say, because it shows that when you need this more complex latent model in order to efficiently model the data, then you end up learning a more complex total latent space that allows compositionality. It turns out also that when you have data that's not diverse enough, it leads you away from learning a rule at all. So hierarchical generalization and linear generalization, one of them is the right rule for English, but they're both systematic rules. Whereas memorization, not a systematic rule, but sort of stable, fairly stable. These training dynamics for the out-of-distribution behavior are kind of stable for both, but you can destabilize them if you introduce the intermediate level. The same thing that creates this bimodality can also introduce very unstable dynamics in the task performance. And that's relevant because it means that that things can look like they're not so bimodal or they're not so clustered, when in fact what's happening is, as you see on the x-axis, this degree of oscillation being measured, the variance in the actual training curve, is higher, that is to say, the curve is further out to the right, when you have a more intermediate value for the task performance. In fact, if you look at the stable runs only, it's clearly clustered, only at the extremes. But if you allow for the runs that are still unstable and still oscillating, you can see that they can take on intermediate values, causing the entire distribution to hide this sort of clustering behavior. So now you know that we can have sort of hidden clusters if we don't account for whether a training run is like really finished in this sense, whether it's actually still unstable. And when we want to understand this kind of instability and and inconsistency in terms of the optimization process, which is clearly, now we know what's going on, what's actually happening, it turns out, is that there are multiple solutions on the training surface, as you would expect. The loss surface has multiple basins, and a basin will contain all of the models that tend towards a particular categorical solution. And there are barriers on the loss surface in between pairs of models that are sort of tending towards the same solution, towards different solutions, rather. These basins are just like convex regions that express the sort of the whole of all of these different models that all have found that same solution. So it turns out if we accept that there are sort of approximately convex, low-dimensional regions that the models are settling into with a shared solution, yeah? Oh, okay. Then what we know is happening is actually that we're escaping all of these little saddle points into different basins. There are saddle points all over the place in these high-dimensional spaces, and so I'm just going to show you a clear situation where these saddle points and their sort of consequential phase transitions can also be hidden. So it turns out that training dynamics are maybe looking smoother than they secretly are because of these, the density of these saddle points. And what do I mean by that? Well, in a sort of simple arithmetic sort of task where we want to say there are several skills that are being learned. There's the skill of like handling the thousands place versus the hundreds place versus the tens place, and there is the skill of carrying a digit over to the next place. You can see in these curves that there are pretty substantial differences between the digit level skills, that those seem to dominate the training dynamics and change when phase transitions happen. But if you look at the loss, there's actually not really significant differences between the loss curves associated with like different carrying or not carrying for a particular digit. It turns out that if we cluster on the loss, we can recover some information about the digits, but if you look at the shading, you can see that they are pretty heterogeneous clusters in terms of the carrying skills. And what's going on here seems to be that in the full rank loss, the exact loss metric, we're eliding little phase transitions that are happening during the escape from these very like high frequency or dense multidimensional sort of saddle points. And what I mean by that is, as you can see over here, as theta goes along this red line, if we say, oh, it's an average of a bunch of like little sigmoids, then the sigmoids eventually add up into a smooth curve. So if we instead try to break down the entire space into a basis, so let's say over here the B1 and B2 basis vectors, which I'm not going to go into detail about how we pick that basis, but basically, if you look at individual basis vectors, the top eigenvector of the Hessian, for instance, contains a distinction between digits. The thousands place skill is clearly in a different cluster from all of the other digits. But if you go to the next vector, actually you recover very homogeneous clusters in terms of the carrying skill. So you can discover these different skills along different basis vectors, and they have different phase transitions with different timing because those skills are recovered at different times, but only in a way where you can discover it by looking at individual linear directions during training. Okay, so that's the entirety of pretty much what I have, but what I want you to take away is that these are really useful sort of distinctions when we think about things in terms of categories instead of smooth, continuous curves. And you might be missing out on a lot of them because clustering effects might be hidden in your samples across different training runs due to different training instabilities. And breakthroughs might be showing up secretly in specific directions. So I would say we should be looking at more variation across training runs when we're doing science. This feels very obvious, I think, to those of you who are maybe like cognitive scientists who actually do statistical tests, but a lot of people in AI don't. And we should maybe be thinking about the low-dimensional projections during optimization. Anyway, okay, questions?
Thank you, Naomi. Yes, we have time for one question. Can we get a microphone over there?
Can you hear me? Yeah. Thank you for the interesting talk. I was just curious how different optimizers like Adam versus SGD, say, or even like parameterizations fit into these pictures. Because one can imagine that, yeah, different architecture have different landscapes and different dynamics, right? And yeah, just how those things like fit.
That's a great question. I think pretty much all of these experiments were done using Adam. And it's entirely possible that escaping from these saddle points with that kind of variation is like reliant on that kind of adaptive momentum. Whereas but I suspect you would see something similar in SGD, but what counts as a threshold sort of point in terms of the data and the size of the model might change significantly. Yeah.
Thank you.
Okay, to give folks enough time for lunch before our keynote at 2, we will break here. Naomi will be here, so I'm sure you have probably more questions for her. Thank you, Naomi, again, and see you at 2.